seems to be holding up. So now the rest of the time I'm going to talk about the energy, and as we heard from the provost, this is really, I think, one of the most important problems that we face globally. You can sort of take a negative view of that, or you can say, well, that means it's worth solving. And I'd like to take that means it's worth solving problem and see if we can't avoid the Malthusian catastrophe. And it's not just a question of supply. We obviously have to worry about what the environmental impacts of energy production, distribution, and use are. And those environmental impacts, whether it's the impacts of damming major rivers or CO2 emissions or SOx and NOx emissions, they all have an impact that may narrow down our options in terms of energy supply. There are security implications of energy supply and scarcity. Certainly we see that very sharply today with the challenges in the Middle East and the Ukraine. There are underlying energy dimensions to those problems that are very real. In the case of the Ukraine, one of the big levers that Russia has been exerting over the Ukraine is the natural gas supply, and one of the reasons that Europe has been really conflicted about how to respond to that challenge is because that natural gas goes through the Ukraine to Europe. So that has a geopolitical implication. And similarly, obviously, with the Middle East, the instability there, at a minimum, raises petroleum prices. And in the worst case, it can actually threaten the stability of supply. That's why the prices are sensitive. Something like 25% of the world's petroleum goes through the Straits of Hormuz, which is the relatively narrow body of water in the Persian Gulf. And on one side of the Persian Gulf, you have Saudi Arabia, and on the other side, you have Iran, and the instability that you're seeing in that part of the world, in a certain sense, is driven by the fact that if you look at the petroleum distribution and demand maps around the world, petroleum is a resource where most of the petroleum is not where most of the people wanting to use it are. And therefore, all the people who want to use it have an interest in what goes on in a part of the world where most of it is, and that leads to all kinds of geopolitical game theory playing out. And we've been seeing that in the Middle East really since the beginning of the petroleum age, with the British and the French making a map that made no sense in terms of where the people were, but made a lot of sense in terms of carving up petroleum resources after the First World War. So there are definitely national security implications, and I think if you look at some of the moves that China has been making in terms of its energy infrastructure, although you can see, for example, benefits on the environmental side of increasing your deployment of wind energy and so forth, a big driver is actually not so much the environmental impacts, it's the national security imperatives of domestic supply. There are clearly economic consequences, and this comes from the fact that, and I'll show a little bit of the data on this, basically our standard of living is exactly tied to our per capita energy consumption. If you plot a graph of energy consumption per capita versus GDP per capita as a function of time all around the world, it all falls on more or less one universal curve. As you get wealthier, you consume more energy, you use it to heat and cool your homes, you use it to travel, you use it to produce the comforts of modern life. If you don't have that energy, you don't have that standard of living, you don't have that wealth. And so if energy prices go up in real terms, then that will have a consequence in terms of the standard of living that people enjoy and the overall economic productivity of any economy. And then finally, the fourth dimension of the challenge is energy access in developing nations, and of course that's related to this one. A large fraction of the world's population is actually still almost without energy. There's something like 1.5 billion people who do not have access to electricity at all. and are living in very primitive standards of living. And there's, of course, a lot of people in the developing world who have limited access to energy, and there's huge demand there, and people want to enjoy, all the attributes of modern life, and that's going to put a lot of pressure on pricing. It's going to put a lot of pressure on national security, and it's going to put a lot of pressure on environmental impacts. So all these things are coupled together. They're not independent, but they're all very good reasons why this is an important problem to work on. And so this just talks about the kind of dynamic in terms of population growth and energy use. So if you look at the kind of UN projections for population growth, which, remember, that's the part of the prediction that Malthus got right. So this is probably approximately right, and because it's, in a certain sense, it's human nature. I don't think we're going to stop people totally from reproducing. So what you see over time between 2010 and 2040 is a growth, and going on beyond that. The models tend to show population stabilizing at about 9 billion. And the reason that the models show some stabilization is as countries become wealthier, population growth does level off. As people get more educated, they have access to birth control, various other things, population growth tends to level off, and you see that in most of the developed world. So you can imagine reaching some kind of equilibrium if everybody enjoys a standard of living and an educational level and access to medicine and so forth, where it would level off at about 9 billion, compared to something like 7 billion, which is where we're sitting now. So we actually have two problems. One is there's another 2 billion people who are going to want some energy, and that drives an energy growth. But you can see that the people is the population curve, the bars are the energy curve. You can actually see that the energy projections are growing faster than population. And the reason that the energy projections, which are measured in quadrillion BTUs or quads, grows faster than population is because the second variable is this standard of living or wealth variable. And you have a lot of the world that's developing economically very rapid. So in addition to having more people, a larger fraction of them are pushing to enjoy a higher standard of living. And so that means the total world energy consumption goes from about 500 quads to closer to 800 over this same 30-year time frame between 2010 and 2040. So the first question is, where do you get that missing 300 quadrillion BTUs? And even at this point in time, you have not even if the population levels off, you have not saturated the energy demand. If you took that 9 billion people and had them enjoy a standard of living equivalent to Western Europe, Japan, or North America, then in fact you'd need a whole lot more energy than that. So first question is, where do you get it from? Are you fighting over a declining finite resource? And the second question is, if you don't change the mix of energy, then CO2 emissions will grow by about 46% over this time frame. And we know that that's the wrong direction for CO2 emissions because of the linkage to climate change. So that's sort of putting a scale on the problem. And this is a significant amount of energy, even if you didn't have to worry about CO2. If you have to worry about CO2, then that means we're not getting energy in this amount in the right mix. So the amount of new energy supply or improved energy supply is both the shortfall here and a significant fraction of this existing energy supply, which is 80% fossil fuels right now. And there's no way around it. When you burn fossil fuels, you make CO2. That's where the energy comes from. It's oxidation. Now, what about CO2 emissions and climate change? And I did not put this slide here because I knew that there would be a typhoon immediately south of us. But it's one example of one of the sorts of risks associated with climate change. And those dimensions that I talked about in terms of the energy problem all manifest themselves also in terms of the impact of climate change. So you have economic impacts. Rising sea levels, can be a problem with inundation in low-lying areas, things like river deltas, for example. There's an awful lot of the population that is living close to sea level and therefore vulnerable. And in addition, even if you're not, Florida might mostly disappear, and that's probably not a good thing if you live in Florida. But even if you're in an area where, it's not immediately overwhelmed by the sea, you're more vulnerable to storm surges when you have things like these large storms. And of course, that's what you saw with, in the US, we had Hurricane Sandy that had a devastating effect on the New York, New Jersey, eastern seaboard area. And it was really the storm surge and the volumes of water that were pushed into low-lying areas, and that gets worse as the sea level goes up. Almost all the climate models predict an increase in extreme weather, and one of the challenges with thinking about climate change is that people don't experience the climate. If you ask someone to worry about a 3 or 4 degree change in average temperature, they'll probably look at you and say, why should I worry about that? Temperature today is, 25. Last week it was 35. Next winter it's going to be 10 degrees. 3 degrees, 4 degrees C doesn't sound like a lot when you see temperature fluctuations from day to day, from week to week, from month to month, much, much larger than that. The thing people care about is weather. Weather is the storm, weather is the rainfall that means your agriculture is viable or not viable. And that 3 or 4 degree change in average temperature that sounds so innocuous, it changes weather patterns. It changes weather patterns in global ways. And it also, because it's in the upward direction, means you're storing more energy in the atmosphere. And that energy releases itself often in the form of extreme weather events. And so that's why you see this increased frequency of extreme weather events. So you shift, if you think of weather, of climate as a probability distribution of weather, it's got some variability that's the weather forecast every day. The extreme weather events are in the tails of that probability distribution. So even though you may shift the peak in the probability distribution by a small bit, if you go out into the tails and say, what's the increase in frequency of these rare events, you can get an order of magnitude increase in frequency of rare events by a very small shift in the position of the peak of the probability distribution. And that's what happens to increase, droughts. Droughts lead to wildfires. This is another form of extreme weather event. And that has an economic consequence. Obviously, agricultural production and energy are impacted if the average temperatures go up. Then you need more air conditioning in Hong Kong and in Tennessee and other warm places. So there's an impact on energy demand. And the agricultural production has to do with those weather impacts. And if you have droughts, California right now is experiencing a very significant drought, and it's having an effect on food prices. Texas drought has already driven up the price of beef. So there's an impact on agricultural production. And finally, the temperature can actually impact productivity and health. Heat waves in Paris and Europe lead to fatalities, particularly amongst vulnerable populations like the elderly. So all of those have economic impacts. They have health impacts. Of course, some of them are related. Obviously, there's an economic impact associated with health and productivity, but it also leads to, as I said, fatalities and so forth. Air quality can be degraded. Water scarcity is something that can have health impacts, and obviously disruptions in supply if there are power outages and that sort of thing, that can cause harm to people. And finally, disease may be more easily propagated, particularly insect-borne diseases, for example. And then security impacts. There's actually a pretty strong correlation, it turns out, between social unrest and food prices. If you look at the Arab Spring, where you had changes in government in a lot of the Arab countries, those were preceded by increases in food prices. It's maybe not a direct cause, but the increases in food prices have an impact in terms of just how stressed people are. If you have to spend a significant fraction of your weekly wages on food, and then that food price goes up and places your family at risk, you're not going to be happy. And that can translate into social unrest. And obviously, if there are agricultural impacts from climate change, that can actually lead through food prices to social unrest. You may have forced migration because of things like rising seawater or droughts that make it not viable to live in parts of the world that are losing their water supply. A significant fraction of India's population gets its water from the snowpack in the Himalayas, just as in California most of the water comes from the snowpack in the Rocky Mountains. That's dwindling. We can actually measure how much it's dwindling, and some places that have large populations may not be viable for those populations, and then the people have to move. And where do they go? Are they welcome? That can lead to conflict. And finally, water supply is already a source of some conflict in some parts of the world. How does CO2 emissions connect to energy? Well, this is probably the simplest way to look at it. So what this shows is CO2 emissions per capita, and this is in metric tons per person, versus energy consumption per capita in gigajoules per person. And actually, the implicit variable for most of this is GDP. So, for example, you can see in the developing world, as a function of time, pretty much, you're moving from the lower left-hand corner to the upper right-hand corner. As your GDP grows, you're using more energy per person, and because almost all of that energy comes from fossil fuels, the CO2 emissions are growing in a pretty linear sort of way. Now, it turns out in the developed world, the time variable is not marching inexorably to the right. And the reason is, in the developed world, at a certain point in development, the linkage between GDP and energy consumption gets a lot weaker. And in fact, in the US, there really hasn't been a coupling of energy consumption and GDP growth since the 80s. So the US curves, you can sort of see it went up and then kind of stalled out. GDP kept growing, but energy consumption stopped growing, and therefore CO2 emissions kind of leveled off. Unfortunately, they leveled off at a very high level. But the CO2 emissions per capita in the US haven't been growing in recent years, and that's because although the economy is growing, the efficiency or the energy intensity of the economy has been improving. Now, the reason that these are coupled together is because almost all the energy comes from fossil fuels, typically 80%. Now, it turns out you can see some variability here in terms of, what's the slope of the curve. This line might be the sort of average if you looked at all the countries are sort of on this curve that has to do with kind of 20% fossil fuel, 80% fossil fuel. Now, it turns out, first off, it matters which fossil fuel. So, for example, coal has a higher CO2 emissions per gigajoule. And in fact, that's why China's growth has been sort of on the steep side. That's because so much of the energy has been coming from coal-fired power plants. In the US, actually, this data stops in 2011. If you look at the more recent data, the US has actually begun to drop down. And the reason the US is dropping down is because natural gas has become very inexpensive because of new technology and extraction, fracking, horizontal drilling, and hydraulic fracturing. And natural gas has a lower CO2 emission per unit of energy. So the more recent data for 12, 13, and 14, which are really the years where we've started to see the impact of natural gas, have begun to pull you down on this curve. But there are two countries in particular that you can look at that are on rather different curves than the rest of the world. And in the developing world, the country that's on a somewhat different curve is Brazil. The reason Brazil is got lower CO2 emissions for the same, and actually you can see it's a fairly significant, if you compare Brazil and China, it's about a factor of 2 difference per person in CO2 emissions. So even though it doesn't look very large on this scale, it's a big difference. And the reason is because Brazil gets almost all of its transportation fuel from biofuels, from sugarcane. And it turns out sugarcane, unlike corn, which is how we make our biofuels in the US, sugarcane is a very advantageous source of fuel because basically you absorb the CO2 to grow the sugarcane, so when you emit the CO2, when you burn the ethanol, it's kind of a closed cycle. So there's not a lot of net emissions associated with sensible biofuels. And Brazil, because of its geography and climate and so forth, is in a sort of fortunate position where they've been able to take advantage of that, and as a result, their CO2 emissions are quite a bit lower than you would guess based on the stage of development of their economy. The other kind of outlier is France, and the difference is not quite as large as Brazil, but if you compare France to other countries with similar, Germany, for example, and actually Germany is moving in this direction now. But the reason France is much lower in the curve, and it's about 60% you can see of other similar countries, is because 80% of France's electricity comes from nuclear energy, which again has lower CO2 emissions. So what this tells you is that you're just using existing technology, you can actually make a pretty big difference in terms of the amount of CO2 emissions. That's something that's encouraging because it means we have some good options already that we know work. Now, they're not being used for a variety of reasons, and some of those might be technology related, but there's clearly nothing fundamental. In terms of the standard of living and quality of life between France and Germany, you wouldn't say there was a big difference. And actually, similarly, between Brazil and its peer countries, again, you would say, kind of comparable, but there's obviously an advantage in terms of CO2 emissions. Now, it turns out, even if you could get everyone down onto this kind of a curve, you're still probably not doing enough to mitigate CO2 emissions. And to get substantially down into this sort of a regime where we can all have access to abundant energy but not have unacceptable CO2 emissions, you're going to need some new science and technology. It's not just a matter of accelerating the deployment of things that already work, although we can do an awful lot by accelerating the deployment of things that work. So if you ask the question, how can you get there and support eventually 9 billion people who hopefully someday can all enjoy a high standard of living and a high quality life, but do so without emitting an unacceptable amount of CO2, at some level you could say we have 3 basic choices. If you want to be not constrained by finite resources. One is nuclear fission, eventually with a closed nuclear fuel cycle. Right now we have plenty of uranium. We probably have enough uranium in high-grade ore to last for something like 70 to 100 years, depending on how rapidly reactors get deployed. But at some point in time, you could have a resource constraint in terms of uranium. However, you have options when that happens. One of them is to recognize that you're only using a few % of the stored energy in the uranium the first go-around and go into a closed fuel cycle, which would be essentially indefinite. Now, to do that, there are still some technical challenges. There's no fundamental feasibility question, but there are social acceptance questions. Obviously, there are some countries that have backed away from nuclear entirely, and even in countries that are still planning to use nuclear, closed fuel cycle and breeding is still not necessarily accepted because there are concerns of what the implications are for nuclear proliferation and nuclear weapons. So there's some social acceptance challenges, and then what it would really cost to go to a fully closed fuel cycle is still really to be determined. Because it hasn't been done at scale yet. Demonstrations of various aspects of the technology. And And actually, you do have to worry about water requirements in terms of the cooling of nuclear power plants. That's not a fundamental issue, but it becomes a limitation when you start thinking about siting and so forth. So that's one option that could support, long-term, a high standard of living for a stabilized global population of 9 billion people. Another option is, in a certain sense, all the things we call renewables are actually solar energy. Whether it's direct photovoltaic conversion of solar thermal for using heat, which is more efficient than photovoltaic currently because you use pretty much the full spectrum. In photovoltaic, you're using kind of a slice. Or biomass, wind is effectively driven by solar. So the things we call renewables are all driven by the inflow of energy into the earth from the sun. And that's actually important because remember I said conservation of energy. This is not a closed system. We have all the time an inflow of energy, and if we could use more of it, then we would have some good options. Now there are challenges here. One of them is land use. Wind and solar have a relatively large footprint in terms of land use, although you could argue that rooftop solar is using land that's already been used, so it's maybe not so bad. You've got to have a transmission and distribution infrastructure because that land that has the attractive properties in terms of incoming solar energy may not be where the people are. In the case of biofuels, one of the challenges is competition with food crops. If your agricultural land is primarily feeding people, you may not have capacity to turn that into energy. Now that depends a lot on where you are. In the US, actually, there's a lot of agricultural capacity that's not, potential agricultural capacity that's not devoted to food production. And so US is fortunate in terms of the amount of arable land and water. It has a lot of latent capacity. Same is true in countries like Brazil and Argentina and so forth. Less true in countries with a high population relative to land mass or a high population relative to clean water. So this one depends on where you are. Another challenge is intermittency for most of these. The sun shines when it's sunny and it doesn't when it's not, and it doesn't at night. And the wind blows when it's windy and it doesn't when it's not. So we'd like to have our power when we want it. And then there's an overall question of efficiency, which couples in, obviously, right now the conversion of solar into usable energy is actually very inefficient. If you look at a total system conversion, it's improving. Photovoltaics in real total system efficiency are kind of around 10%. Solar thermal is better. Biomass is even lower because of the, first you've got to do photosynthesis, then you've got to harvest it, then you've got to convert it and so forth. So the efficiency is not so great. The offset for that is there's a huge amount of energy, so you don't actually have to be totally efficient. A few percent is plenty if you could do that at scale. And then finally, your third option is fusion. Fusion has really no fuel supply constraint at all, for all practical purposes. So you don't even have to, go to the sort of complexity of fission with closed fuel cycle. Fusion is how the sun works, and we're not short of hydrogen. But the problem with fusion is we're not even sure if it'll work. So unlike with fission, where in principle we know we can do all the things we would need to do a closed fuel cycle for nuclear fission, with fusion we still don't know whether or not we can actually make it work as a practical method of extracting energy. The only case we know we can make work is thermonuclear weapons, and that's not a particularly useful device from the purposes of energy production. So there's questions of scientific and engineering feasibility that we need to address before we can even begin to ask the question, okay, maybe it works in theory. Is it practical from a point of view of cost? We're not even ready to ask this question yet. So I'm going to talk a little bit about all of these in kind of the time that's remaining. I guess I got about